The focus of this lecture will be on differential positioning or differential GPS systems, otherwise known as DGPS. So just a brief background on your GPS error budget. There are many different sources of error and each contributes a different magnitude of error. So differential GPS is a way to partially correct for errors that are common between the rover and the base station GPS receivers. So there's several different types of automatic and manual DGPS. There's wide area augmentation system or WAAS. There's continuously operating reference stations or cores, or you can set up your own base station and correct from that. On the right here you see a distribution of discrepancies or errors in a measured position. So the average or center of those locations is a green dot, and commonly it's assumed that your errors are distributed equally in all directions. In other words, it would be the blue error budget. However, in reality, we see that many times our error budget is not perfectly uniform in all directions, but rather is elliptic in some direction. So there's several different types of units that you can use for GPS, and we've covered a little bit about this in previous lectures. The simplest is a single frequency unit, which under best conditions has about 10 meters of error, and that's with a timing error of about 20 nanoseconds. The next step up from that is going to be your commercial systems, and those are traditionally the ones that incorporate more of a DGPS capability. Remember that multipath error introduces or can introduce up to about 15 meters of error depending on the surrounding environment, and that PDOP is the geometric strength of the satellite configuration and reference to a particular time and location. So differential GPS, as I said previously, is a way to partially correct for errors that are common between the roving and base station receivers. And essentially DGPS is a way to improve your position and timing performance of handheld units. In order to utilize differential GPS, you need to have a dual frequency unit. What this means is that it can receive the high frequency satellite signals as can any other GPS receiver, but it can also receive a low frequency radio signal that's transmitted from the base station and received by the roving GPS receiver. So DGPS works by using measurements from a stationary receiver at a known location. This is called your base station. So here in the diagram you see your base station on the left side of the diagram. You calculate your known errors at that location, and optionally you can transmit those real time or you can do the correction after the fact. But either way, you have that receiver at a stationary known location, that's your base station. You estimate clock errors continuously at that base station, and then you apply those correction factors, or you calculate correction factors from those clock errors, and you use those to correct measurements from another GPS or multiple GPS receivers. Those are called your roving GPS receivers. So one way it can work is you have a GPS receiver or your base station pointing to with a red arrow here. It broadcasts the signal it receives from a known position. So essentially what it's doing is it's averaging its location, or it's situated over top of another previously surveyed well-defined benchmark or location. The GPS unit in the field, which is the roving receiver, simultaneously receives GPS data from the satellites as well as the other receiver, in other words your base station, through a radio signal that's transmitted by the base station. Now that base station is, once again, remember, transmitting that correction factor continuously. That GPS error from the known station or from the base station is then compared to that of the receiver at the unknown location, and that correction factor that it calculates is applied to the roving GPS location. So remember, differential GPS or DGPS is only a partial correction, and the amount of error corrected for is related to the distance between the rover and the beacon and the similarity in environment between the receiver and the beacon. So this operates on the assumption that many GPS error sources are highly correlated over both space and time. So if we look at the diagram on the right, we're assuming essentially that the two red dots on Earth, the errors are correlated at both those locations. So this assumes, in other words, that the error at both the permanent and the roving GPS site will be the same. So the error at the base station is subtracted from the coordinates given for the roving GPS. Now it's important to note that DGPS doesn't account for local errors, only common PRN errors, so pseudorandom noise errors. And this is a partial, not a perfect correction. Remember, it doesn't account for local effects. Satellite clock errors are a slow linear change in position. In other words, there's always error in the satellite clocks. That's something that's predictable and changes linearly, which we can account for. There's also ephemeris errors that we need to account for. Those are once again a slow linear change in position, but that depends on the location of the rover from the base station, or in other words, the location of the rover relative to the base station. So there's also tropospheric errors, which are the signal varies with temperature, pressure, and humidity. Remember, transmitted through the atmospheric layer. And once again, this depends on the position of the rover station relative to the base station. And this is due to different angles to the satellite can introduce a small error. Remember, the angle between the satellite and the receiver determines how much of the atmosphere that signal has to be transmitted through. So if you have a different angle to the satellite from the base station to the satellite and from the roving receiver to the satellite, that can introduce error due to the tropospheric error. There's also local weather variations, which are unknown and by and large uncorrectable. So that's something that you need to account for when designing your survey. There's also potentially a difference in elevation of the rover and the base station. This can introduce a rather large error. If you think about it, you're assuming that a correction factor calculated at the base station is valid and applicable to that of the roving GPS receiver. However, if you have a significant difference in elevation, let's say the base station is higher than the roving receiver, then that base station is going to receive that signal earlier and is going to calculate a different correction factor that when you apply that then to the roving GPS measured locations is not appropriate. So here we could see an example where the local variation in temperature, cloud cover, and water vapor would affect your ability to apply a differential GPS survey. Now in this case it's rather extreme, but you get the point. The idea is that variations in the troposphere will also affect your ability to carry out or conduct a DGPS survey. So there's ionospheric errors, which the signal varies with total electron content of the ionosphere and the signal angle. So remember we talked about tropospheric errors. It's partially dependent on the angle between the satellite and the receiver. Once again, ionospheric errors are very similar in that respect, where the error depends on the separation distance between the rover and the base station, but also is partially dependent on that angle from the receiver to the satellite. Now, ionospheric errors can introduce a change of up to 8 centimeters in the mid-latitudes and anywhere from 65 to 300 centimeters in the high and low latitudes. So once again, if we look at our error budget, the measure location of the base station is different from the actual location. So the black dots here represent individual measurements of a base station location, and the green dot represents the average of those locations, or the average location of that base station. So we can see the error budget in reality is not perfectly spherical, but rather is elliptic in some orientation. So now we're going to talk about different modes of differential GPS or differential positioning. The first is real-time DGPS. This is primarily used for navigation, by ships and boats when coming into and leaving a harbor, getting closer to the coast, or water hazards. This is done because the ships need as accurate location as possible real time. So the timing corrections are sent from the base station to the roving receiver through a radio link. Now there's no correction for receiver errors such as multipath, which remember could potentially introduce up to 15 meters or so of error, and those corrections are common to both receivers. So those beacons are continuously operating, and they're located along the coast, and they're operated by the Coast Guard and the Army Corps of Civil Engineers. So beacons along the coast are operated by the Coast Guard, and beacons along navigable rivers belong to and are operated by the U.S. Army Corps of Engineers. Most coastal areas in the northern hemisphere have access to differential GPS data from these beacons. You can see the map on the lower right here where you have a global distribution. However, they're more concentrated in the northern hemisphere, these beacons are. If we look here at how there's overlap between the different beacons, we can see that there tends to be more overlap along the coast and along your major rivers, even including up into the Great Lakes. That's actually rather hazardous as far as navigation goes, and so it's important that we have this differential GPS to assist mariners and shipping for navigation purposes. So real-time kinematic is a term that you'll come across quite frequently, otherwise known as just RTK. Another name for this is carrier phase enhancement, or CPGPS. That's not going to be as common as you might find the term RTK. And what this is that those differential corrections from the base station are transmitted or broadcast via radio waves to the roving receiver, and they're applied in real time, hence real-time kinematic. So on the left here we see an instance where a base station is situated over a known point and it transmits that correction factor. On the right here we see that base station is over a free point, and what it does is it's going to calculate its average location. Here on the right we can see the base station is over a free point, and in fact the roving receiver goes around to one or more known points. Post-processing kinematic surveys, or PPK surveys, are ones where the base station computes the timing errors and stores those to a disk actually. So instead of transmitting those real time, you're going to then take that stored data and download it from the roving and the base station receiver, and the software, which is often proprietary unfortunately, is going to take that correction factor, it's going to compute a correction factor from the base station and apply it to your roving GPS coordinates. PPK surveys are actually more accurate than RTK surveys, simply because the volume of data used to calculate your average location or used to calculate that correction factor is larger in a post-processing survey. Static DGPS surveys, there are several different types. There's single differencing, which is where you have one satellite is observed from two different receivers. In that case, the satellite clock error is eliminated only. The receiver clock error is not eliminated. You also have double differencing, where two satellites at least are observed from two receivers, and in this case you have the receiver clock error is eliminated. There's also triple differencing, where two satellites are observed from two receivers at two different points in time, or epochs. So the next two slides are going to go through an example of demonstrating why DGPS is really important. So in particular, I want to point your attention to the roads, the major highways on this map. Now, if we look at what that route looks like collected without differential GPS turned on, which is the case on the left here, we can see that there's several instances where the route jumps all over. In other words, where that GPS is assuming or measuring a different location than where it's actually at. Now, if we use a base station and correct this data, which you see on the right here, you can see that the route is much smoother. It's much more true to the true location or the true route. Now we're going to go into a little bit of information about satellite-based augmentation systems, or SBAS. There are several different types of SBAS, and the most common one that you're going to deal with is the Wide Area Augmentation System, or WAAS. That's primarily used in North America. However, it's also important to note that Europe, India, Japan, and there's several commercial systems also exist, depending on the location that you're working in, and I'll explain a little bit more about why. So first, a little bit more about WAAS. WAAS stands for Wide Area Augmentation System. It was developed by the FAA, or Federal Aviation Administration, for improved GPS navigation during all flight phases, including approaches. In 2003, WAAS signal was activated for the general aviation, which covers 95% of the U.S., including areas of Alaska. And this system enhances GPS measurements by measuring and correcting the satellite signals. So it's a way to improve the accuracy of the receiver positions. And similar to the GPS system as a whole, it also has 3 segments. So it has the ground, has a space, and it has a user segment. This should look very similar or sound very similar to the GPS system as a whole. So WAAS operates by a series of geostationary satellites, specifically put up for this augmentation system. There's a control station on the west coast and a control station on the east coast, and it operates as an augmentation to your traditional GPS constellation. So here we can see the GPS satellites and some of the Wide Area Reference Stations, or WRS, and the Wide Area Master Stations, or WMS, as well as the 4 uplink stations present. So the ground segment is composed of multiple Wide Area Reference Stations, or WRS, which send data, GPS data, to 3 of the Wide Area Master Stations, or WMS. Now, the WRS are survey locations which monitor WAAS geostationary satellite signals and relay that information to the WMS via a ground communication. So in 2007, there were 38 WRS present and active. You can see the list here. It's not only throughout the US, but as well as Mexico, Canada, Puerto Rico. So the WMS use that WRS data. They generate corrections, both fast and slow. So some of the fast errors that they correct for or account for are higher. So fast errors are those with a higher priority, and they affect the GPS satellite instantaneous positions, or clock errors, and they're applied instantly by any receiver. The slow errors, on the other hand, are long-term ephemeris and clock error estimates, such as your ionospheric delay, and those tend to be applied after the fact. So WMS passed the correction data onto 2 pairs of ground uplink stations. Remember I said there was 4 total, there's 2 pairs each. And these GUS, or ground uplink stations, transmit that data to the satellites. That information is then transmitted back down and picked up by the user segment. So the space segment is 3 geosynchronous communication satellites. So there's Inmarsat 4, Galaxy 15, and Anik F15. And you can see the orbits on the right here in red, white, and yellow. And they operate over the Pacific Ocean region and the Atlantic Ocean region. So they're more targeted towards North America, South America. These satellites receive GPS satellite corrections, both fast and slow, from the ground uplink stations. Those corrections, remember, are then transmitted back down to the user or to the receivers. So the user segment is composed of you yourself with any GPS that's WAAS enabled or WAAS capable. So GPS units first use the satellite data that's being picked up by the receiver to determine its location and current time. Then WAAS works if the GPS unit has capabilities and is enabled on the unit. The GPS receiver then immediately applies a fast type of correction data, in other words, corrected satellite position and clock data. After that position is determined, the receiver begins to use the slow correction to improve the accuracy. So slow correction, remember, an example of that is ionospheric errors. So now that we've gone through WAAS, you should understand a little bit more about how these different WRS, WMS, the ground uplink stations, and the geostationary satellites work in conjunction or as an augmentation system to the traditional GPS system. We're now going to go into GBAS, or ground-based augmentation systems. So one of the most common ground-based augmentation systems that's widely spread is called a continuously operating reference station, or CORS. Now, CORS is composed of hundreds of stationary, permanent operating GPS receivers, and these are in very well-defined, pre-surveyed locations throughout the U.S. and actually all over the world. And what these do is they continuously receive GPS radio signals and integrate their positional data. The post-processing using the CORS data can allow you to get sub-meter positioning. However, this requires special software to complete these error calculations, and you need to use 3 or more nearby stations. Now, also interesting to note, you can utilize a system such as this, some of the more modern systems, with either a base station that you set up, or you can actually Bluetooth with your phone and log into the CORS network and get that correction factor and use that in real time in conjunction with your survey. So here we can see one application of this is surveying and mapping, where up top here, that yellow disc is the receiver, and there's a cable running down into the guy's backpack, and then there's a data logger that he's plugging information into. Now, this is used for surveying and mapping of construction sites, utilities, and a whole wide variety of other applications. So differential GPS also depends on the amount of data that you collect, especially with regards to post-processing. So if you have 10 minutes of data, say for example, you might be able to post-process to within 0.3 meters accuracy. If, for example, you increase that to 30 minutes of data collection, you can improve your positioning to 0.1 meters accuracy. 45 minutes of data at the base station, you can improve that to 0.01 meters accuracy. And if you have 48 hours or more of post-processing, or in other words, of measured locations of that base station, then you can post-process your roving receiver locations to within 0.001 meters. So it largely, for post-processing, depends on the sheer volume or the time in which that base station is collecting data. And this is once again because it can more accurately calculate that correction factor through time and calculate how that correction is going to change through time. So if we look at the accuracy levels of a whole wide variety of different surveying and GPS systems, we can see that our recreational grade or our autonomous handheld units, such as the ones distributed throughout the class, typically cost $100 to $500. In the case of the ones currently available to you guys, they run in that range. However, the accuracy of those or the error of those is much, much worse. When you increase to mapping grade, which have a regional correction or differential correction, you improve your accuracy. You also add a little bit of cost. When you increase your mapping grade equipment to sub-meter, now you have a local differential correction occurring, and you can further improve the accuracy of your survey. However, as you see, the cost is jumping dramatically. So now you're from $100 to $500 all the way up to $4,000 to $5,000. The higher grade is a survey grade, which includes a local base station, and this costs anywhere from about $11,000 to $50,000. So the cost can escalate very quickly. However, it also depends on the application. So if you are primarily mapping utilities and you need that high degree of precision, you may choose to go with a survey grade GPS system just based on whatever contract you were awarded. However, if you don't need that level of accuracy, you're simply doing this as a recreational user, a handheld recreation grade unit might work great. It just depends on your application and the required level of precision and accuracy. So there's several differential correction sources. I said most of them tend to be commercial or proprietary systems. The UCGS beacons are completely free, and I provide the URL for you here. That's terrestrial differential correction. The user provided, it doesn't have a cost or URL. That's basically your own base station that you set up. And that's going to depend on whatever model, however old it is, you choose to go with, if you even have one available. There's also SBAS, remember space-based augmentation systems, such as OmniStar, OmniStar HP, Deer Starfire 1, Deer Starfire 2. You can see the cost of those is anywhere from $500, $800, up to $1,500 a year. Those are commercial systems. WAAS, remember, is also a SBAS, but it's completely free. So DGPS applications, why do we need differential correction? We said it's important in terms of navigation for ships or for planes, but what are some other applications? DGPS is used extensively in dredging. So when the Army Corps of Engineers comes in and they are looking at dredging a particular harbor or channel, they need 2-meter accuracy in order to position their dredges very precisely, in order to keep these navigable waterways open. So you can see on the left here and on the right, there's several different types of dredging operations that you can use. However, they still need that high degree of accuracy, and DGPS is how they get that degree of accuracy. It's also used in precision agriculture. Precision agriculture, for those of you who are not aware, is an incredibly lucrative business. It's continually increasing. It's a multi-million-dollar industry that's continuing to grow and will continue to grow. DGPS is used in precision ag systems by enabling the farmer to more efficiently use the land. So here you can see a field, and say the red line or the line running throughout here is where the equipment ran. On the top is part of a field mapped with differential GPS. Conversely, on the bottom you can see the rows are all over the place. This is a case where they attempted to use GPS. However, they didn't have that differential GPS. They didn't have that high degree of accuracy and precision. So it's really important in precision ag to use differential GPS systems. And I'll talk about this in the next lecture a little bit more specifically, how those systems work and what are some of the advantages or disadvantages to this application. So with selective availability set to 0 and under ideal conditions, GPS receiver without WAAS can achieve up to 15-meter accuracy most of the time. That's dependent on the satellite geometry, the open sky view, and no other user-induced errors. Remember, selective availability is no longer around. It was discontinued. So ideally, without WAAS, under good conditions, you can achieve an accuracy of 15 meters. However, under ideal conditions with WAAS, just simply adding the additional augmentation system, the user can achieve a 3-meter accuracy 95% of the time. So it's not going to be every time, but it's going to be 95% of the time you can get within plus or minus 3 meters. So a regular GPS unit might give you an accuracy of plus or minus 15 meters. When you enable WAAS, you can get within plus or minus 3 meters. Continuously operating reference station, you can push that down even further and finer accuracy. And with your own external base station, that's when you're going to get the greatest accuracy in your positioning. For additional information, here are a couple of useful links. Trimble Survey Systems has a tutorial on differential GPS and how it works. The FAA heads up the information about WAAS. Remember, that was operated or initiated by the Federal Aviation Administration, and they continue to have a heavy hand in operating and managing that. Now you should have a better understanding of how differential GPS works, what the principles are behind it, what the assumptions of it are, as well as what the different types of SBAS and GBAS are. So you need to know what WAAS is, you need to know what CORS is, you need to know what the different levels of accuracy are with the different types of augmentation system, here covered near the end. And you should have a better understanding of how DGPS can be used to effectively survey a given area, but also what some of its disadvantages are and what some of the costs associated with it are. So remember, the application or the purpose of the survey is going to dictate what level of accuracy you need or want, which is going to dictate what equipment you need, and that's going to dictate your cost.